Distinguished guests and dear friends, good evening. Welcome to the Mathematics Night of 2026 ICBS. My name is Gan Ziying from Tsinghua University. It's a great honor for me to be the host. Tonight we are all gathered here in Beijing to spend a wonderful night belongs to mathematics. So now let me introduce the distinguished guests joining us tonight. They are ICBS Chair, Fields Medalist, Chairman of the Board of Shanghai Institute for Mathematics and Interdisciplinary Sciences, Professor Xin-Tong Yao. Welcome. (2026) ICBS Emmy Noether Medal Laureate in Mathematics, Director of Research at Centre National de la Recherche Scientifique, Professor Claire Voisin. Bienvenue. (2026) ICBS Xinsheng Chen Medal Laureate in Mathematics, Merton Professor of Mathematics at Harvard University, Professor Hongze Yao. Welcome. (2026) ICBS Andrew Wells Medal Laureate in Mathematics, Eugene Higgins Professor at Mathematics at Princeton University, Professor Shou Wu Zhang. Welcome. Professor at Shanghai Institute for Mathematics and Interdisciplinary Sciences, Professor Christopher Brav. Welcome. Please allow me to once again extend our sincere gratitude and a warm welcome to each and every one of you for joining us tonight. It's mathematics that brings us together. Now let's move on to the first session. We are pleased to welcome three distinguished professors to deliver their general lectures and share the latest research findings. First, let's welcome Professor Hongze Yao. Welcome.
Thank you. So I would like to just a second. So my lecture, I will talk about random metric theory and its application. Now, how do I do up and down? Oh yeah, here. Sorry. Now, the story started in 1955 with Eugene Wigner. He was just a second. Now, Eugene Wigner, he has answered the question of what's the spectrum of uranium's nuclei. So he was faced with a picture like this. Oh, sorry. He was faced with a picture like this. Just let me go back. And he wanted to explain that how this. Can you hear me? No problem. Okay. How this spectrum looks like. Why it looks like this. And the question is the Hamiltonian for heavy nuclei is very difficult to solve. So it was almost impossible to answer this question. And let me remind you, 1955 is more than 70 years ago. So he came up with the idea of using the random matrices to describe such a phenomenon. And now the random matrices is, I explained in the morning, but let me repeat it again. It's a matrix satisfy Hermitian conditions. It can be either real or complex. And it has a mean 0 and the variance 1 over n. And the variance 1 over n is normalizations. And if the metric element Hij normal distribution is called the Gaussian ensembles. And so there are two cases. In the complex case, called the Gaussian unity ensemble, and in the real case, it's called the Gaussian orthogonal ensemble. Now, so the Wegener has, so this is a famous quote of Wegener. When I first saw it, I find this extraordinary. What he says is the following. So he said, perhaps I'm now too courageous when I try to guess the distribution of the distance between successive levels of energies of heavy nuclei. So theoretically, the situation is quite simple if one attacks the problem in a simple-minded fashion. The question is simply what are the distance of the characteristic values of a symmetric matrix with a random coefficient. So this was, I hope that every young people remember this sentence, because he was faced with a question, want to solve a Hamiltonian of n-particle system with two-body potential interactions. On the other hand, he just declared that the question can be solved in this way. Just compute a random matrix, and you look at the eigenvalues, the distance between the eigenvalues, and that's the answer. And the Freeman-Dyson says the following: you picture a complex nucleus with as a black box in which a large number of particles are interacting according to an unknown laws, because you don't want to know what it is. But now, so today I will tell you how successful this is and how much this influences research even today. So the Wegener prover theorem says called the Wegener semicircle law, and which is the probability distribution, the density of eigenvalues look like semicircle. But on the other hand, if you look at the distance between the eigenvalues, look at the distance between the eigenvalues, and now you can see that because you want to put n eigenvalues between -2 and 2, and so the typical distance is 1/n, and you can blow this up, and once you blow this up, and now you want to know what the probability distributions of this distance. So what we're going to claim is a probability distribution of this distance is actually give you the probability distribution of heavy nuclei. This was a claim. Now, without proving any theorem or without thinking it as a mathematics, you should understand how bold is this claim. And you can do similar things at edge, but instead of scale like n, you will scale like n to the 2/3, and there are some calculations you will do it. And this is called the Tracy-Witten law. And Tracy-Witten did his computations much later. Now, so this was Wegener's claim at the time of 1955. Now, at the time when Wegener first looked at these problems, actually, the probability distribution of the Gaussian case, this is so-called sine law, is not even known. Because at the time, the Wegener cannot even compute the probability distribution of a Gaussian case of this large random matrix when the matrix size go to infinity. So this is not a simple question. This computation was actually done by Goldin and Mehta, and it's not an easy computations. So let me tell you a story. It's actually Wegener at the time. He computed 2x2 Gaussian case, and you should think about how crazy this is. He first think about his n-particle Hamiltonian, and which was impossible to solve. He declared this is just a random matrix, and the random matrix problem he cannot solve either. And then he take a 2x2 matrix, Gaussian matrix 2x2, and you compute the distance, the probability distribution of the two eigenvalues, the distance of two eigenvalues. And this is called a Wegener surmise. And the Wegener surmise, if you compare Wegener surmise and the modern day computation of the distance between the probability distribution, it actually matched up to 98%. So this was incredible achievement. And now, so today the random matrix, there are so many examples, including, you will see the example in mathematical physics like Anderson models, and also in the free probability theory, and even in the statistics, and also in the neural network, and also in the graph theory. Then a famous question people are asking in graph theory is what's expander. So today I was trying to say something more about this part related to graph theory. Okay. Now, so you can summarize the Wegener's idea as this Wegener great universality hypothesis. It says the eigenvalue statistic of random matrices, it will serve as a universal law for highly correlated system. And now, so with this, so the meta-state problems, if you take a random matrix, if the probability distribution of each metric element, suppose you don't use Gaussian, you just take arbitrary probability distribution. Do we know that the eigenvalue distribution will be at the end, as matrix goes to infinity, it will be independent of the law of each metric element. And this is called the Wegener-Dyson meta-conjecture. And then this conjecture was proved to be correct in after you can see that the conjecture was made in 1967. It took truly a long time to answer this question. So this says so this defines something called a Wegener universality class. It tells you that a matrix eigenvalue distribution will be the same as a GOE or GUE. And now, without going into details, so I want to show you that I want to show you that there are other metrics also belong to this Wegener universality class. And now, this page is about delocalization and the QE of eigenvector. So because the time constraint, so I will not explain detail of this. Roughly speaking, it will tell you that the eigenvector, eventually the probability distribution of eigenvector will become flat. And this is a concept called the quantum unit ergodicity. And now, the Wegener's idea is not that, I mean, today every physicist, as far as I know, believe that what Wegener claims is correct. But at the time, when Wegener proposed this idea, there are a lot of there are objections, and the most famous objection is George Uhlenbeck. He asked the following question. He asked that if you admit that Wegener ensembles give a completely wrong answer to level densities, why do you believe any of the other predictions of random matrix theory? So this was, the semicircle law is not universal, because if you take a different system, it will not always say semicircle, as you are going to see in a minute. But on the other hand, the probability distribution of the gap is universal. So this is something very strange. As a first order, this semicircle is not universal. On the other hand, if you look at if you zoom in, look at the distance between the eigenvalues, the its distribution will be universal. So after that, now today we can prove there are many metric ensemble belong to this Wegener universality class, and there are many examples, including this free probability theory. And but today, what I want to say is about, most important is about the deregular graph, and this will be the main focus of this lecture. Okay. Now, there's a general question you can ask is, how much randomness you need to get random matrix statistics. Because if you look at Wegener matrix, it's an n by n matrix, and so you need n squared randomness. So if you have n squared randomness, you will get a random matrix statistics. So this is understood. So this was really just WDM conjectures. And now, if you look at something called a matrix which is a bit more skinny, it's called a band matrix. And the band matrix, the randomness is n times w, because the width of the band is w. So this w is bandwidth. So the band matrix has randomness is about n. It's n times w, and you think w is basically finite. So this was about n randomness, and this is band matrices. This was also understood because this was proved that band matrix also obey the random matrix statistics. And then you can also ask, what about random graph? The random graph is that if you take a d-regular graph, the number of randomness in the d-regular graph is basically size of order n. And you can also ask the Anderson model, but on the other hand, Anderson model, we still don't know completely why this will obey the random matrix statistics. But you can even go further to ask the same question about, in the case of quantum chaos conjecture, and also about the most famous question is the Riemann zeta function. The local statistic of zeros of the Riemann zeta function, again, is claimed to be random matrix statistics. But here is completely, in these two cases, completely deterministic. There's no randomness. So even the case of no randomness, one still expect the random matrix statistic actually is going to be correct. Now, this was a famous quote by Freeman Dyson when he saw the Montgomery at the Institute for Advanced Study in 1972, when the Montgomery showed him what he believed the statistics of zero zeta functions. And Freeman Dyson says, extraordinary. Do you realize that's a pair correlation function of for the eigenvalues of a random permission matrix? It is also a model of the energy levels in a heavy nuclide, say uranium-238. This was extraordinary conversation. Now, this was a so-called, this one was the quantum chaos conjecture. The conjecture is, again, it's about the eigenvalue distributions of the Laplace operator in this domain. And if the Bilias, the classical dynamics is chaotic, then one expects that this is going to be random matrix statistics. All right, so let's go to the random d-regular graph, which was I want to explain today. Is if you consider a d-regular graph. D-regular graph means the d means the number of edges from each vertex. So if you take a d-regular graph, and now you put a probability distribution of all possible d-regular graph with n vertices, and this is called a random d-regular graph. I don't think I have time to say about Erdős Rényi, so I will focus on random d-regular. And then there's a correspondence between the graph and the matrix. Is you construct an adjacency matrix by putting a 1 between when I and j are connected with the edge. Now this is called an adjacency matrix. And now this adjacency matrix is going to satisfy the Keston-McKay law. The Keston-McKay law is a probability law look like this. This is not the semicircle. You can see that when d is equal to 3, it looks like this. And you can see that it's not exactly semicircle, but when d becomes larger and larger, it starts to look like more and more like a semicircle. All right, so there's the first eigenvalues, lambda 1, which is will be bigger than 1, bigger than 2. And now the eigenvalue, we label the eigenvalue from the largest one to the smallest one. So the lambda 1 is the largest one. And now, so there's a concept called expander of a graph. The expander of a graph, the expander is a way to measure the connectivity of the graph. And typically it's measured by Cheeger's constant. And then there's an inequality between Cheeger constant and the spectral gap between the gap between the first two eigenvalues. And then there was also a theorem by Noga alone says the eigenvalue, except the first one is bigger than 2 minus the constant divided diameter of the graph. But because the diameter goes to infinity, so this proves that lambda 2 in the limit is bigger than 2. So Noga alone conjecture that the lambda 2 will be the second largest eigenvalue will be 2 plus a little over 1. And this was proved by Freeman in the 2004, and his error correction is 2 plus something, and this something is a log n divided by log n squared. But actually, so there are some further work of this, but the key question is, so maybe I'll skip this. It's don't really have much time. I think how much time I still have? Okay, all right. So let me skip this and go to this definition of Ramanujan graph. So the Ramanujan graph is the optimal spectral expander because we just saw that the eigenvalues will be 2 plus a little of 1. But so the best possible is actually eigenvalue has to be less than 2. So eigenvalue has to be less than 2, and then this Lubelsky, Phillips, and Peter Sarnak, they define a regular graph is Ramanujan if all the eigenvalue beside the first one is absolute value less than 2. Is called Ramanujan graph. And the name Ramanujan comes because in their proof they use part of these Ramanujan conjectures. And now, so they use they construct explicit the Ramanujan graph with d equal to p plus 1, and p is a prime mod equal to 1 mod 4. And so this was done by Lubelsky, Philip, and Sarnak, and Margulis at the same time in 1988. And then there are other progress here I didn't really cite, but another main progress is Marcus Spielmann and Srivastava. They prove the existence of infinite family of bipartite deregular Ramanujan graph using the method of interlacing polynomials. So Peter Sarnak they conjecture that the second largest eigenvalue will become a Tracy-Widom distribution if you normalize it correctly and make some shift. So you can see that there was some, if you look at the simulations, actually if you adjust it correctly, it seems they look like the same. So this was a conjecture in 2004. And then, but on the other hand, at the time the Noga alone and Sarnak, they believe in a completely different story. What they believe is Sarnak believe that if you take a deregular graph at random, none of them will be Ramanujan. And on the other hand, for Noga alone says almost all the random deregular graphs are Ramanujan. I think they believe in this because come from their proof, and this was a natural conclusion from their proof. All right, so the theorem we prove this Sarnak and Miner Novikov Sabelli conjecture completely. We find that there's no shift, so there's no constant shift, but the other constant a can be computed explicitly. This will converge to the Tracy-Widom law, and now so the probability for the graph to be Ramanujan becomes the probability in the Tracy-Widom function is less than or equal to 0, and now because Tracy-Widom function has 83% to be probability to be less than 0. And now you take a square, you get 69%. So the 69% is a probability that a random deregulated graph is the Ramanujan graph. Okay. All right. So this is concluded this part of a deregulated graph. And so the summary is, let me give you the summary. The summary is these Wigner's ideas is starting from asking about the nuclei spectrum. It becomes, has so much influence on so many areas of mathematics and in application, and including in many different areas, including even nowadays, most people believe that this the zeta function zeros actually are connected to random matrix statistics. And also there are many things I didn't say is about the KPZ universality, and also there's also connection with nonlinear case or nonlinear random matrix and neural networks, and also the random graph are connected to the random surfaces. So all these are very active research area. So I'll stop my lecture here. Thanks a lot. Thank you.
Thanks again for Professor Hongze Yao for the illuminating lecture. So now let's welcome our second speaker, Professor Claire Voisin. Welcome.
So okay, I stay here. Okay, so I was not sure what subject to choose, so I decided to speak on the very classical subject. I mean, the starting point of algebraic geometry, which is Riemann surfaces, and this is still a very alive subject. How does it work? But it's not. Okay, thank you. Okay, so I'll start with the very beginning. A priori, so the story goes back to Riemann. Riemann surface, it's an object that comes from Riemannian geometry. So it's you start with an oriented compact surface, and you put it on it metric. And this is a case where the data of the metric defined a complex structure on the tangent space. Because the tangent space is two-dimensional. And then by solving the Cauchy-Riemann equation, you get local holomorphic coordinates that makes your Riemann surface into a complex manifold of dimension 1. So here the picture shows genus 1 and genus 2 Riemann surfaces. So they are as a topological object. The genus G, so it is on the picture, it's a number of holes, but it can be given a better, more rigorous definition from topology by saying that the number 2 minus 2G is the Euler Poincaré characteristic of X that is computed using the Betti numbers that come from algebraic topology. And in fact, there is another way, which is more inside algebraic geometry, or complex geometry, of computing the number G, namely, thanks to the Hopf formula, the number 2G minus 2 can be also computed as the number of zeros of a holomorphic one form. I said there is a local holomorphic coordinate Z, so you can make sense of a holomorphic one form. And well, assuming that maybe the genus is at least 1, you have non-zero holomorphic one forms, and you consider the number of zeros of them. That gives you the number 2G minus 2. For the theory of Riemann surfaces, the most important object that comes next is that of a holomorphic line bundle on X. So a complex line bundle on a topological space, well, you imagine over each point of your space, you have a complex line, and you want, of course, to have local trivialization. So locally, your fibration into lines, it's just a product. And there are transition functions. So for a topological line bundle, your transition function will be simply continuous. But to have a holomorphic line bundle means that the transition function, you have local trivialization with transition functions that are holomorphic. Now, it turns out that this is not totally obvious, but there are plenty of holomorphic line bundles on a compact Riemann surface. And they are crucial if you want to construct your compact Riemann surface as an algebraic variety. And the way we can construct, maybe it's not the only one, but one way to construct holomorphic line bundles is to say by looking at the associated sheaf of holomorphic sections, and over each open set U, you look at the set of holomorphic sections of your line bundles. That gives you a sheaf. This sheaf should be a locally free sheaf of OX model, which is of rank 1, so that is locally isomorphic to OX. And then if you start with a number of points on your Riemann surface, x1 to xd, you consider the so-called ideal sheaf of these points, that is the sheaf of holomorphic functions that have to vanish at this point. This is locally free of rank 1, so this gives you a line bundle, and in fact the dual of it will be, so the notation is OX of x1 plus xd. This is a certain line bundle, holomorphic line bundle on your Riemann surface. Now, next, again, so there are notions that come from topology, but also from, that you can see also via algebraic geometry. The degree of a line bundle, you can define it via topology by considering the first Chern class. This is coming from topology, and then integrate the first Chern class over X. That gives you a number. This is the degree. But you can also construct the degree from the viewpoint of algebraic geometry by taking any, so maybe there are no non-zero holomorphic section, but there are always a non-zero meromorphic section. Take a meromorphic section of L, non-zero, and then count the number of zeros, or number of zeros minus number of poles. That will give you a number, and that is also the degree. And this is called the Lelong formula that says that it's also the two definitions agree. And the example that this line bundle OX of x1 plus xd that I mentioned before, it has exactly degree d because exactly by definition it has a holomorphic section which vanishes exactly at the point xi. And this is another way to characterize this holomorphic line bundle. Next, all this is of course extremely classical, but now I want to explain quickly what is the modern proof of the Riemann embedding theorem that shows you that this Riemann surface that I started with a topological object with a complex structure, that in fact this object is algebraic. So for this, I add the notion of sheaf cohomology. So let me not say, so it's the hi of xn, it's a i's cohomology of X with value in the sheaf of holomorphic sections of L. So you have to know what is the sheaf cohomology. It's a very modern, modern contribution to the subject of algebraic geometry. Very crucial or central, the building contribution. And let me not explain what it is, but the important point is that the H0 of XL, this is the set of holomorphic sections of the line bundle on X. And the Riemann-Roch formula, it is old, but in modern terms, it is stated as follows, that if you have a line bundle, holomorphic line bundle on your X, then it's the Euler-Poincaré characteristic chi of XL. By definition, it's a difference between the H0 of XL, the number of independent holomorphic sections, minus and H1 of XL. So this number this is the Riemann-Roch formula. It is degree of L plus 1 minus G, and G is the genus of X. So to make this still more useful, it's better to know what is the H, to compute the H1 of XL, and it turns out that there is the Serre duality that tells you that this space H1 of XL, this is degree 1 cohomology, you can compute it as the H0 of a canonical bundle of X twisted by L minus 1. So in fact, the two spaces are dual. This is called Serre duality. And as a consequence, we get vanishing, namely that the degree 1 cohomology of X with value in L vanishes if the degree of L is at least 2G minus 1. It's because then the H1 of XL, it is the same as the dual of H0 of X, Kx tensor L minus 1. So I didn't say it, but Kx, it's a canonical bundle of X. So it's a sheaf of holomorphic one form. And as I explained by the Hope formula, the degree of the canonical bundle is 2G minus 2. So now if your degree of L is 2G minus 1, the degree of Kx tensor L minus 1, it will be negative, so there cannot be any non-zero section. And so now out of this, we conclude quite easily the proof of the modern proof of the Riemann embedding theorem, which one formulation is this, that if you have a line bundle L on X, which is of degree D at least 2G plus 1, then by taking holomorphic sections of L, so there are D, by the Riemann-Roch formula, there are D minus G plus 1 independent holomorphic sections. These sections will provide a holomorphic embedding of X into the complex projective space CPN. So specifically, you choose a basis sigma 0 to sigma n of your space of holomorphic sections, and to a point X of the Riemann surface, you associate the n plus 1 upper sigma 0 of X to sigma n of X. Of course, the sigma i's are just sections of a line bundle, but if you change the local trivialization of your line bundles, all the sigma I of X, they will be multiplied by the same number, and finally, in projective space CPN, you will get the same point. So that's really, and to make the story still really complete, and in the story, the journey from starting from a complex geometry or even Riemannian geometry to algebraic geometry, you have to add sorry, I didn't finish the statement of the Riemann embedding theorem. So if you have your line bundle of degree at least 2G plus 1, these sections, they provide a holomorphic embeddings that realize your X as a complex submanifold of dimension 1 in projective space CPN. But then there is another very important theorem of the 20th century, namely the Chow theorem, that tells that a compact complex manifold of complex projective space is algebraic. It's absolutely remarkable. That is, it is defined by algebraic equation. That means that arrived at this point, we can consider our Riemann surface as a completely different object, namely an algebraic variety of dimension 1 defined by algebraic equations. And I would like to discuss now the algebraic geometry of small genus curves. And in fact, it is very well understood, again, thanks to the Riemann-Roch theorem. So I am going to discuss genus 4 curves because genus 3 is simply too easy. There is an important notion, that the notion of a hyperelliptic curve. So the hyperelliptic curves are different. They are those curves that can be obtained as a double cover of a projective space CP1. And it is known, I mean, it's not that hard to prove, that a curve is not a curve of genus at least 2 is not hyperelliptic if and only if using the sections of the canonical bundle, the holomorphic sections, that is the global one form, you can embed X into PG minus 1, and G is the number of holomorphic sections. And so let me speak about non-hyperelliptic curves, those that can be realized, that have a canonical model inside projective space PG minus 1. There is an important result due to Noether. I believe it's Max Noether and not Amy, which is that if you consider a non-hyperelliptic compact Riemann surface or a smooth projective curve of genus at least 3, then the multiplication map from, so you consider, if you consider the product of 2 sections of the canonical bundle, you will get a section of the line bundle Kx tensor 2, which sometimes we denote this by 2Kx. And this multiplication map, multiplication of sections, is surjective in the non-hyperelliptic case. And knowing this, plus the Riemann-Roch formula, you easily get a complete description of what is a non-hyperelliptic curve of genus 4. First of all, we get as a corollary that if X is a genus non-hyperelliptic genus 4 curve, canonically embedded in P3, it is contained in a single quadric, which furthermore is irreducible, that's obvious. Why a single quadric? It's because to say that it is contained, so you consider the restriction map from degree 2 polynomials on P3 to sections of 2Kx on the curve. On the left, you have quadratic polynomials on P3, and the space has dimension 10. And on the right, you have the space of holomorphic sections of 2Kx, and by Riemann-Roch, I gave the Riemann-Roch formula, this number is 9. The map is surjective, and so the restriction map has a kernel of dimension 1. This kernel, it gives you one quadric vanishing on the curve. So that proves the first corollary. And the second corollary, it's exactly by the same counting argument, namely that X is my genus 3, genus 4 curve, X, has to be the complete intersection of a quadric and a cubic in P3. And again, it's by the same argument, the Riemann-Roch formula gives you the number of sections of the line bundle Kx tensor 3. And now you look at restrictions from the space of cubic polynomials restricted to the quadric. This is what I denote by H0 of Q or Q of 3. It's just a notation. That means cubic polynomials on P3 restricted to the quadric. Now this number is very easy. The dimension of this space is 16. While Riemann-Roch tells you that the space H0 of X 3Kx has dimension 15. That means that on your quadric, there is an extra cubic equation vanishing on the curve. And so the curve must be contained in this intersection of a quadric and a cubic. And then you just look at compare the degrees, and you see that the curve, so it is contained in this intersection, but it must be equal for degree reason. That is the complete, both means the curve canonically embedded has genus has a degree 6, and the complete intersection of a quadric and a cubic also has degree 6, so they have to degree. Okay, so what is important now is, so I don't know if there was some noise, so that doesn't mean anything. So now there is a point, a general fact about the geometry of quadrics, the two-dimensional quadrics, is the fact that we are over an algebraically closed field. So the equation of, well, generically the quadric Q is smooth. That means the quadratic equation is non-degenerate. And so because we see the algebraically closed, the equation can be taken in the form x0, x1 plus x2, x3. And then you see immediately that there are plenty of lines in the quadrics, namely, for example, x0 equals 0, x2 equals 0. That gives you a P1 contained in the quadric. And you can make a variation on that. And in fact, you have an explicit map that I wrote here, phi, from the quadric to P1 cross P1, and the fibers of these maps, they correspond to lines contained in the quadric. So we say that the quadric has two rollings. So you have one parameter family of lines given as the fibers of phi 1, and the other one parameter family is given as the fibers of phi 2. So in any case, so there are all of these lines, and because the curve is defined by a cubic equation inside the quadric, this cubic equation restricted to the line, they vanish at exactly 3 points, it's cubic, and that means that all these lines, they intersect the curve into 3 points. So we say that the curve is trigonal in two different ways, namely you consider the two restrictions phi 1 and phi 2 from the quadric to P1, you restrict them to X, and that gives you two maps of degree 3 from the curve to P1. Okay, so now I want to discuss more the general subject of which is related, namely the Jacobian, what is the Jacobian of a curve, or it turns out it's the same as the Picard variety. In general, if you consider any smooth, complex projective variety, well, of course, I could do this more generally in the algebraic setting, but let's say complex. Then you consider the set of isomorphism classes of holomorphic line bundles on L on X with a trivial first Chern class. So C1 of L equals 0. So and this is a set. A priori, it has a group structure because when you have two line bundles, holomorphic line bundles, you can take the tensor product of them. That gives you the abelian group structure. And in fact, this variety, it's an abelian variety that is, if you like, a complex torus that is also a projective variety. So there is a general proof inside algebraic geometry of that statement. That is essentially once you prove that if you can endow it with the structure of an algebraic, of a projective algebraic variety, once you know that it has furthermore this abelian group structure, it follows that it is an abelian variety. So you can do it like this inside algebraic geometry, but inside from the viewpoint of complex geometry, you can do it by Schiff cohomology, by using the famous exponential exact sequence. It is a wonderful tool to do computations in in the Hodge theory and algebraic cycles on complex algebraic varieties. So you have this exact sequence from the sheaf of a holomorphic function, takes the exponential that goes to the sheaf of an invertible holomorphic function, and the kernel will be the sheaf of locally constant functions with value in Z. And when you do the long exact sequence of cohomology associated to this short exact sequence, you get, so you want, there is in the middle H1 of X, OX duo, a star, that is a degree 1 cohomology of X with value in the sheaf of invertible holomorphic functions. And it turns out that this object, it is the same as the Picard group of X, that is a set of isomorphism classes of holomorphic line bundles, just by considering the transition functions as giving 1 cocycles. And so at the middle you will have pic X, which is H1 of X, OX star, going to H2 of X, Z. But it turns out that this map, it is the first Chern class, and the kernel, it is H1 of XOX modulo H1 of XZ. And this object, it's a complex vector space, quotiented by a lattice. And so this is a complex torus, and then you have to show by some way that it is algebraic. And now let us speak about moduli. Moduli is a very important subject that was not really understood in full generality at Riemann's time, but I mentioned that in my case of genus 4 curves, the moduli of genus 4 curves, or non-hyperelliptic genus 4 curves, I described it for you because I told you genus 4 curves, it is the complete intersection of a quadric and a cubic. So you say, just want a parameter space for the complete intersection of a quadric and a cubic, and that can be very well done. Of course, you have to make the quotient by the group of automorphism of a projective space P3, but we are this way. I mean, in the case of small genus, the moduli spaces are totally explicitly understood in terms of geometric invariant theorem. And now, so we have this moduli space that means each point parameterize a curve. Over this moduli space, we have the universal genus 4 curve. So the fiber of this map for the C to M4, it is called the universal curve of the genus 4. And then associated to this fibration, there is the associated Jacobian fibration, namely over each point of the moduli space, the fiber will be not the curve, but it's a Jacobian or it's a Picard variety. And now the link with what I explained before. I said the genus 4 curves is contained in essentially canonically in a quadric, and canonically that gives you 2 line bundles of degree a priori. It has a group structure because when you have 2 line bundles, holomorphic line bundles, you can take the tensor product of them. That gives you the abelian group structure. And in fact, this variety, it's an abelian variety that is, if you like, a complex torus that is also a projective variety. So there is a general proof inside algebraic geometry of that statement. That is essentially, once you prove that if you can endow it with the structure of an algebraic, of a projective algebraic variety, once you know that it has furthermore this abelian group structure, it follows that it is an abelian variety. So you can do it like this inside algebraic geometry, but inside, from the viewpoint of complex geometry, you can do it by sheaf cohomology, by using the famous exponential exact sequence. It is a wonderful tool to do computations in the Hodge theory and algebraic cycles on complex algebraic varieties. So you have this exact sequence from the sheaf of a holomorphic function, takes the exponential that goes to the sheaf of an invertible holomorphic function, and the kernel will be the sheaf of locally constant functions with value in Z. And when you do the long exact sequence of cohomology associated to this short exact sequence, you get, so you want, there is in the middle H1 of X, OX duo, a star, that is a degree 1 cohomology of X with value in the sheaf of invertible holomorphic functions. And it turns out that this object, it is the same as the Picard group of X, that is a set of isomorphism classes of holomorphic line bundles, just by considering the transition functions as giving one cocycles. And so at the middle you will have pick X, which is H1 of X, OX star, going to H2 of X, Z. But it turns out that this map, it is the first Chern class, and the kernel, it is H1 of XOX modulo H1 of XOZ. And this object, it's a complex vector space, quotiented by a lattice. And so this is a complex torus, and then you have to show by some way that it is algebraic. And now let us speak about moduli. Moduli is a very important subject that was not really understood in full generality at Riemann's time, but I mentioned that in my case of genus 4 curves, the moduli of genus 4 curves, or non-hyperelliptic genus 4 curves, I described it for you because I told you the genus 4 curves, it is the complete intersection of a quadric and a cubic. So you say, just want a parameter space for the complete intersection of a quadric and a cubic, and that can be very well done. Of course, you have to make the quotient by the group of automorphism of a projective space P3, but we are this way. It's, I mean, in the case of small genus, the moduli spaces are totally explicitly understood in terms of geometric invariant theorem. And now, so we have this moduli space that means each point parameterize a curve. Over this moduli space, we have the universal genus 4 curve. So the fiber of this map from C to M4, it is called the universal curve of the genus 4. And then associated to this fibration, there is the associated Jacobian fibration, namely over each point of the moduli space, the fiber will be not the curve, but it's a Jacobian or it's a Picard variety. And now the link with what I explained before. I said the genus 4 curves is contained in essentially canonically in a quadric, and canonically that gives you two line bundles of degree 3 on the quadric. But the point is that you have two of them. So when you make the difference of the two line bundles, the D1 minus D2, that will give you a degree 0 line bundle, but it is defined only up to sign. Because I made a choice, I ordered, I choose first the D1 and then the D2. I could as well do D2 minus D1. So in fact, I get a section of the Jacobian fibration, but not on the moduli space M4 itself, but on a double cover. A double cover which consists for each genus 4 curve, non-hyperelliptic, to choose one of the rulings of in the quadric, and choosing one the rulings that gives you also an ordering between D1 and D2, and then that determines this line bundle, degree 0 line bundle, D1 minus D2. And then on this double cover, what I constructed, in fact, is a global algebraic section of the Jacobian fibration. And now In fact, one cannot do better because of the so-called Francetta conjecture, which is in fact a theorem that is true in any genus, that says that let's do for genus at least 2, if you consider the, perfect, thank you. If you consider in general, the universal curve over the modular space of genus G curve, and then you consider the associated Jacobian. You want to study the algebraic holomorphic or algebraic line bundles on the total space of C of this family. The Francetta conjecture says that the only line bundles that exist, they are the multiples, the tensor products of the relative canonical line bundle. So said like this is not completely true. The Picard group of the universal curve modulo the obvious line bundles that come from the base, pi upper star of the Picard group of MG, that is cyclic, generated by the so-called relative canonical bundle. So you take the relative canonical bundle. It's also the relative cotangent bundle. So it is a dual of the relative tangent bundle. So it is a line bundle. So it's a beautiful result. And this result tells you in particular that there is no non-zero section of the Jacobian fibration, because a non-zero section of the Jacobian fibration over MG, that will give a line bundle on the total space, which will have a degree 0 on the fibers. And that by the theorem, we know that those that are of degree 0 on the fibers, they come from MG, so they should be trivial on the fibers. And so I finish my talk. But I explained that in genus 4, of course, the Francetta conjecture applies, but still the construction made in the previous slide tells you that there is a section not of G4 over M4, but of the so-called associated Kummer fibration, K4 over M4, where K4, you consider the Jacobian fibration and you take the quotient by plus or minus 1. And as I said, the D1 minus D2, it was well defined, but up to signs. So globally, that will give a section of this Kummer fibration, K4 over M4. And the result, I want to finish by a result of myself, is that in fact, the only rational sections of the Kummer fibration over M4, they are given by multiples of this section that I call the Griffiths-Pirola section. So this statement that I proved recently was conjectured by Pirola, and curiously, in genus at least 5, it is still open whether the only rational sections of the Kummer fibration over MG are the 0 section. In genus 4, we have this exceptional section of the Kummer fibration, but we don't expect that it exists in higher genus. I'll stop here.
Thanks for Professor Voisin. Merci infiniment. Now let's welcome our third speaker, Professor Shou Zhang. Welcome.
Thanks. So this is a Mathematics Night. We're not talking about mathematics. I talk about some story. Before I open my lecture, I would say that it's really amazing to get this to award this Andrew Wiles Prize. The reason is that 2 years ago I come here to introduce Andrew Wiles, and now I get his prize. And Andrew Wiles was my colleague, in fact, my mentor when I was at Princeton. And then when he left, I took his position. So now I get his medal. And but today's lecture has something to do with him too. So before Anois proved his Fermat theorem, I was working on the ABC conjecture. And because I want to prove Fermat theorem. And since he proved Fermat theorem, then I moved to something else. Well, that's for Wednesday lecture, you're going to see what I'm working on, the Grozagi formula. And the Friday lecture, you will see, I didn't prove ABC conjecture, but I've done something else. So anyway, this is, so today is, it's not, I'm not talking about anything I proved. I talk why I like ABC conjecture, why this is a really amazing problem, even I don't know how to prove it. Okay. So this is a story about we talk about story from Euclid to Diophantus, Fermat, Shapiro, Master, Osteller, and Wiles. So this is basically the sequence of story. It's a very simple equation. It could be asked 2,000 years ago. But the question is, if it was asked 2,000 years ago, maybe we don't know how to prove Fermat theorem at all, because the equations are too simple. There's almost no way to do it. So equations are very simple. We talk about the equation A plus B equals C. So that's the equation everybody knows. The problem is that this is the additional equation. Now we want to check what is the multiplication will give you. So we want to think of A plus B equals C has something to do with A times B times C. That's kind of a crazy thing, right? Why you want to study addition equation suddenly becomes the products. So addition and multiplication seem to describe completely different operations. You can see clearly, nobody want to do this thing. Well, mathematicians want to do it anyway. So when they do, for a positive integer, we define something the radical. The radical of n, you just take the product, the primes. Forget about the power. So for example, 12 is 4 times 3. For 4, we only take 2. For 12, so the radical of 12 is 6. 18 is 2 times 3 squared, but we only take 3 there. So radical of 18 is also 6. So the two very different numbers, the same become semi-radical. The radical remembers only the primes occur, but ignore how many times they occur. So that's basically the radical. So that, for example, 3 plus 125, 128. So 125 is 5, the cubic of 5. Another is 7 to the power of 2. The radical you calculated is 30. So C is equal to 128, but the radical ABC is 30. So you probably say, well, this 128 is pretty big. Radical can be pretty small. So the question is that, can C be much larger than radical of ABC? Can this happen infinitely many open? So the expected answer is that apart from a rare exception, the answer is no. So radical cannot be too small compared with the C. So this is the conjecture made by Mathel Osteller conjecture. So for any epsilon bigger than 0, there is a constant C epsilon such that for every co-prime triple A plus B equals C, this C, in fact, is not much larger than the product. There's a radical of ABC. It's kind of an amazing thing, right? You know, the radical is just taking the prime, forget about power. You forget about power, and in fact, it already can bound the largest number C there. So this is really very surprising. Addition is constrained by multiplications. If we think about it, multiplication always gets very big. But if we forget about the power of the prime, it's not that much. So this is called ABC conjecture. So ABC conjecture is about the integers. Okay, the points in mathematics, if I learn as I said that when if you do number theory, before you do calculus, it's called elementary number theory. The basic number theory already done by Euclid. Once the calculus was invented, you do calculus. So that's called analytic number theory. Then in the 20th century, then people start that maybe you can apply some geometry. It's just like Riemannian geometry has something to do with physics. Algebraic geometry has something to do with the number theory. So you need to bring the geometry inside. Okay, this is the geometry. First thing you want to do. So we want to say that a simple equation has something to do with algebraic geometry. That's exactly the Claire just described. So they need to have a geometric word to explain that. So in fact, we need a modular space to describe that. So that's the equation you want to do. So the y squared equals x cubed plus x plus b. One equation, one curve, one geometric word. So the key idea that problems about integers can become a problem about geometry. Okay? So how do you do that? So this is in 1980s, my PhD advisor Shapiro proposed a very deep conjecture about elliptic curves. I will not talk about the conjecture elliptic curves. I don't think it's at least at the time everybody getting tired. I don't want to say anything to do with that. If Shapiro conjecture holds, then ABC conjecture holds. So this is the Shapiro conjecture implies ABC. In fact, Shapiro conjecture has a lot of geometric intuition inside. Is David Master and Austell. They're trying to understand the Shapiro conjecture, the proposed ABC conjecture. But this day, people completely forget about Shapiro conjecture. If you forget about Shapiro conjecture, there's no geometry inside at all. Okay, so that's what I'm trying to say. The Master and Austell formulated the ABC conjecture, not isolated the study of A plus B equals C, but as a way to understand the Shapiro conjecture. The birth of an idea, arithmetic and geometry truly meet here. Okay, so this is from this equation, A plus B equals C, you form a elliptic curve, y squared equals x plus x minus a, x plus b. Okay, so in other words, A plus B equals C is a simple affine curve in a plane and the three-dimensional space. For each point of curve, you attach elliptic curve on that. So you basically elliptic fibration in terms of algebraic geometry. So even start as a simplest equation you can get, you still want to do geometry. So a question, okay, so this is what is it doing? So this I wrote something about Shapiro conjecture. We're not going to say anything. What the Shapiro conjecture you to do is something to do about deformations, degenerations, conductors, and modular spaces. We're not going to describe that. I think Claire's lecture already showed enough of this stuff there. And but Claire didn't talk about deformation or singular battle reductions. So the whole point of a geometry is to bring a simple equation, the simplest equation you can imagine in terms of algebraic geometry. So now, why this ABC conjecture is so attractive? Because it implies the Fermat-Lassé equation. So that's basically the equation solved by under y is the xn plus y and the zn. Is solved by elliptic curve and modular forms. The geometry solved a 300 years old arithmetic problem. But I have to admit that when you translate the number theory problem to geometry, it's not finished. You need a final touch. Final touch is analysis, right? So just like a physics problem becomes differential geometry, you still need some analysis to do that. That's basic geometry analysis was Professor Yao's invention. For this diphonic equation, the story is exactly the same. You have a number theory problem, you become a geometric problem, but to solve that, you bring some analysis inside. That's basically what Andrew Weil is doing. He brings the modular forms, right? So that's basically missing when we study the ABC conjecture. So why the ABC conjecture is so important? It offers another explanation of the Fermat-type equations. For example, Andrew Weil only solved the problem xn plus yn equals zn. If I just change a little bit, say AXN plus BYN equals CZN, the Wise method, we're not going to solve the problem, but ABC is going to solve it. Because they bring the equation there, ABC conjecture, you can forget about power. Your Z to the N will be bounded by X times Y times Z. So basically, Z to 3 power, the third power. So from this, immediately, you will get the Fermat equation. The second thing is it's very important. The generalized ABC conjecture would provide a systematic way to solve many Diophant equations. So basically, solve Diophant equation is the human being's dream for the last 2,000 years since Diophant. So can we actually solve equations, right? Give you the equation, in this case, it's just algebraic curve. So basically, it's a one polynomial with two variables, right? This kind of equation, can we solve it? If we have the ABC conjecture, the answer is yes. Yes means that there will be an algorithm, a computer algorithm that solve every equation. That was a dream. But right now, no, we don't know how to solve any equations. We study equations in a qualitative way, but nobody study equations in a quantitative way. So, the third thing is that this ABC conjecture gives you a very deep relation between addition and multiplications. You probably never know before. So that's basically what I say, the 2,000 years dream, given equation, can we systematically find all the rational solutions? So this is why it was so attractive when I was a graduate student. So I visited Paris, 86, then the Bourbaki talk, given by Australia about how to solve Fermat last equation. Of course, it's about this ABC conjecture. So I give you, this is the evolution. So it's a problem about the integers, about the equations, then become curves, then become modular spaces. These we are given the so-called modern arithmetic geometry. So ABC conjecture is not at the end of the story. It's a gateway to the rich landscape. The highest modular space arithmetic algebraic geometry. The deepest idea often begin with the simplest equation. So I just rewrite this thing to you. I hope after today's lecture, you remember a few things, right? There's the elliptic curves. There's a modular space. If you can remember this thing, I'll be very happy. Okay, thank you. So that's basically their conclusion of my lecture. So I'm going to conclude with the Hermann-Weiss words. In mathematics, we are less concerned with what things are than what is the relation between them. So the relation between them is about a simple Diophant equation become elliptic curves, then eventually become a modular form. For second part, you go to my lecture, the Wednesday lecture. I tell you how a elliptic curve become modular form. And that idea can help you to solve Diophant equations. Thank you.
Thank you, Professor Zhang, for delivering such a brilliant story lecture. Like previous years, this year's ICBS has also awarded the Frontier Science Prizes with nearly 100 laureates in the field of mathematics. Today, we have invited 5 award representatives to share their insights on academic pursuit. To begin, let's welcome Professor Kohonda from the University of California, Los Angeles to the stage to deliver his acceptance speech. Welcome.
Hello. Thank you very much for the award, and I'd like to thank all the organizers for such a great conference. I think I'll just tell you a little bit about myself and maybe some tips for graduate students. So my main expertise is in contact geometry, which is somehow the odd dimensional and perhaps less well-known sibling of symplectic geometry. Right? And I got into this subject in the 1990s when basically there was no one working on it, except for maybe now the people who are now known as the leaders of the subject. Right? And as a postdoc, for some strange reason, I made a discovery which actually made me, allowed me to write many papers and got me a job. And strangely enough, as I was thinking about this, it turned out that almost everyone who was working in the subject at that time also became successful mathematicians. So maybe the moral of the story for today is, the way to become a successful mathematician is to be at the right place at the right time. Well, maybe not quite. There's actually one ingredient I think that you need. And so you need to be at the right place at the right time, but you also need to have the right preparation and somehow have the right skill set to seize on the opportunity, right? So how do you develop such a thing, right? So my recommendation for students would be just take your time, learn the things you care about. Don't look up any AI, don't do anything. Just spend time staring off into space. Think about problems that are important. Think about it and try to cultivate your own way of thinking about problems. Okay? And the most important thing is to always think about important problems. I think that's all I have to say. Good luck.
Thanks, Professor Kahonda, for your sharing. Next, let's join me in welcoming Professor Matthew Korn from the Institute of Science and Technology, Austria, to the stage. Welcome.
Hi, thank you to the organizers, and it's a really such a great honor to be receiving these prizes and to have the opportunity to be selected to be one of the few people who are speaking here. Yeah, so I thought, I have just a few minutes, but I will say just a tiny bit about the mathematics. So I was awarded prizes in two categories here, but I think they're sort of part of the same general theme of somehow trying to understand statistical aspects of sort of the space of all objects, where all objects could mean the space of all finite graphs or all combinatorial designs or something like that. And so in particular, one of the things that I did was to study, so combinatorial designs are like set systems with very strong regularity properties. So like a Steiner triple system is a collection of triples, a collection of sets of size 3 of some underlying point set, so that every pair of points is in exactly one triple. So it's like a very regular arrangement of triples. And you can get these things with algebra. So there are many kinds of algebraic objects and geometric configurations which give you these types of very regular set systems. But there's been a really interesting line of work recently trying to sort of pull apart design theory and algebra and try to show that these things really can have much richer structure than just the kinds of things you get from algebraic objects. So yeah, so I was asked to make some reflections, especially for younger people that might be in the audience. And so I think the main thing that I would like to reflect on is the value of collaborations, so I think in combinatorics, we really highly value collaborations, and I've been very fortunate to have some very strong relationships with people who I've continued to work with over and over, and I think it's just been so valuable for me to have people who have complementary ways of thinking, complementary expertise that I can communicate really well with, and we can encourage each other, and I think that's really a huge part of everything I've accomplished. So yeah, I want to thank all of my collaborators, especially the ones on these prize-winning papers from this conference. That's Ashwin Shah, Meta Abswani, Lisa Zauerman, and Michael Simkin for really making all of this possible. Yeah, I think that's all I'd like to say. Thank you.
Thank you, Professor, for your sharing and suggestions for the young students. Next, let's welcome Professor Chao Li from Courant Institute of Mathematical Science of New York University to deliver his acceptance speech. Welcome.
Thank you. I'm very honored to receive this year's award in differential geometry. So, I feel that I may have prepared a little bit too much, but there could be interesting stories, so I'll share with you anyway. I'll basically take this opportunity to talk a little bit about the story behind this awarded paper, because it's kind of an exciting journey. In 2016, I asked my advisor, Rick Shen. By the way, Rick Shen is a student of Professor Yao, and I believe his first student. And so I asked him to give me a challenging problem to think about, right? So we all do this. I all ask this kind of questions to our advisors, and he gave me this so-called K-pi1 conjecture. I don't want to describe this conjecture in detail, but it's kind of a Novikov type conjecture in the differential geometric shape. And moreover, Rick mentioned to me that actually he had this promising strategy with Professor Yao back in the 80s. Okay, so okay, so it's wonderful, right? It's Shen and Professor Yao, the Shen Yao wrote this amazing. So they actually solved this conjecture in 3 dimensions and wrote this amazing survey article in higher dimensions, and they had a strategy in 4D, right? It's and then back then I didn't know much, and we couldn't do anything. But I feel extremely lucky about being in this community, and in a few years as things move on and we have more understanding, my collaborator Otis Chodosh and I actually could carry out the Shen Yao strategy in 4D and extend it to 5 dimensions. So we solved it in these 2 dimensions. So the missing part precisely was a new type of comparison geometry. It's comparison geometry like for curvature conditions, and the new understanding is try to relate curvature conditions to quantitative topology, and in this case the microscopic dimension or Urizen width, whatever it is. Okay, so we solved it, and with this new understanding, we said let's be brave, right, and try to find something else to solve. And so Otis and I then moved on to a related problem, which is actually what got us this award, and it's the so-called the Bernstein problem for minimal hypersurfaces in R4. And the reason we move on to this problem again is due to a guiding principle due to Shen Yao, and basically a stable minimal surface should behave like a in R4 particularly, should behave like a 3-manifold is positive scalar curvature. And that's exactly the right object we could, test our new understanding on. And we worked on that on and off, and we were extremely lucky again that the whole differential geometry community supplied us a kind of a new monotonicity formula, or a new monotonicity quantity that we exactly needed. So on reflection, I'm really grateful that I'm part of this differential geometry community, and there are challenging problems and masterminds behind us. Okay, so now I'm also asked to say a few words to PhD students or generally students. So I'll share with you one story I had. About 13 years ago, I was an undergraduate student, and occasionally I also attend events like this in Tsinghua University. And so we're, later probably we also have this today, but back then we also had this, occasion where we may ask questions to masters, right? So back then I remember I asked Professor Yao, nowadays looking back, it's kind of embarrassing question. But then I asked, which area of math is best? Right. Yeah. The reason is very practical for me back then, right? So, all my friends, my friends in my year, back then the fashionable and trendy areas were algebra and broadly speaking, algebra and number theory, broadly speaking. But I particularly fancy differential geometry and analysis, for instance. And so I got the doubt, and as a young student, I got the doubt. Am I wrong, right, basically? Now, Professor Yao's answer, which I now would deeply echo and want to share with you, is that there's actually no best area, right? That's the so in other words, all areas present challenges and great ideas from great minds. So, so the lesson I learned is that we should be brave and be proactive. And so that's all I want to say. Thank you.
Thank you, Professor Lee, for sharing us the story and your insights. Next, let's welcome Professor Amy Murphy from University of Toronto to deliver her acceptance speech. Welcome.
Hi. So first of all, it's of course quite an honor to receive the award. And so in terms of reflections, there's a couple of themes that have come up at the ICBS that have kind of reminded me of, I've been teaching classical geometry a lot. And so I think there's a couple of cross themes here that I'd like to discuss. So one of these first themes, I guess the first theme is about kind of internationalism and global mathematics. So of course, classical geometry kind of starts with Euclidean geometry, which of course is kind of like named for, a particular kind of like Greek. But when you learn the history more, of course, it's, I think, becoming more well known that almost all of these ideas were known in China, were known in India, and were also known in the kind of Babylonian area, basically at the kind of same time. And so I think having this kind of global perspective is nice. But there's a particular story which is actually related to spherical geometry. And so in the development of spherical geometry, one of the most important things is spherical trigonometry. And so the history of this takes place approximately around the year 1000, I guess, or maybe 20 years after this. And this was developed primarily by a mathematician named Al-Jayani, who was influenced by the kind of like Islamic golden age, but was kind of coming a bit after this. And so he was working and living in what is now Spain. And so there's this really interesting history where, of course, you have kind of like Greek mathematics, and then later kind of like moving to kind of House of Wisdom in Baghdad, but then moving across North Africa and then up to the Iberian Peninsula in Spain. And then later, during the Renaissance, the development of kind of like perspective drawing and things like this was very influenced by this. And so there's this kind of it's not only that mathematics is kind of like taking place in all places, but it's that collaboration where things are kind of moving across, which is kind of really giving us all kind of like better ideas and better science. Yes. The second theme I wanted to talk about is the changing nature of math. And we also see this in classical geometry. So, of course, kind of many cultures were developing kind of Euclidean geometry at the same time, but they had very different perspectives on it. it might be for kind of like land parceling or accounting or for abstraction for the sake of itself. And then, of course, later on, you have the notion of kind of like natural science as a sort of like polymath thing. But mathematics as a kind of like isolated kind of discipline was not yet developed. And of course, then later, there's a famous kind of story about a mathematician Hilbert, who was, in the wake of hyperbolic geometry, was developing an axiomatization for Euclidean geometry. And a big part of this was that in the 1900s, mathematicians were learning that what we considered rigorous before was not really sort of rigorous, and then so we kind of changed our notion of what rigor means. But then even Hilbert's axiomatization, so this is around the year 1900, is not purely formulated in terms of kind of first order logic. And it wasn't really until another mathematician, Tarski, who kind of like fully formulated this in terms of first order logic. So my point is that the notion of like, what does it mean to be rigorous changes. The notion of what mathematics even is changes. And as we've been hearing quite a lot, even in the first day and yesterday as well, we've been hearing quite a lot about the developments in artificial intelligence. And I think not only artificial intelligence, but automated proof checking as well is, again, kind of changing what it means, what mathematics means, what rigor means. And I think that that dynamism to mathematics as it sort of changes through the centuries is really something that is kind of endlessly fascinating. So thank you.
Thank you, Professor Murphy. We truly appreciate your wonderful talk and sincere sharing. Now let's welcome the final speaker to the stage, Professor Yuji Odaka from Kyoto University. Welcome.
Hello. So thank you very much. It's my great honor to receive the prize and attend this precious interdisciplinary wonderful conference. I thank all the organizers, secretaries, and volunteers who worked on this hard. So the prize for us was given to a piece of our work on something called case stability, a notion of algebraic varieties, which I spent much of the time during my earlier career, especially when I was a PhD student. This field was maybe a postdoc time. This field was originally meant to be a bridge between algebraic geometry and differential geometry to different areas a priori. In general dimensions, the subject was pioneered by mathematicians such as Kehler, Calabi, and Professor Yao in the past century. Today, it has become highly international, and the population of the researchers is quite large, including a lot of young researchers. However, so when I started to seriously work on the basics of case stability from purely algebraic side, algebra geometric side, hardly anyone, or maybe very few people were interested in the case stability from a purely modern algebra geometric point of view. So probably my own contribution in the field was to connect it to birational geometry, or compact modular space, compact variety, modular variety, which are major interest in algebraic geometry. That's my part of my work. Looking back, we are quite excited to see the field has expanded a lot with a lot of people. Yeah. So I think I must give some comments to younger people. I think there are various types of researchers, and also people have different personalities. So I think we don't need to put universal rules to follow in general. But having said that, maybe I can tell you just a few words from my own experience. Personally, one thing I always keep in mind is the importance of originality. Avoid a competition in a short time, like a competition in speed. But what is the originality? I think it's hard to define in reality, but still, as a human, I think we can feel it. In the coming age of living with AI, I feel the sense of originality will be even more important. That's what I believe. Solving recognized problems in a recognized way may be exactly the kind of task at which AI is becoming increasingly powerful. And another thing is that when I myself was younger, I was deeply attracted by the artistic nature of mathematics. I felt it artistic in two senses, personally, for its own beauty and as a human activity through the long history. New age will be created by younger people. I hope we can keep this artistic and human aspect of mathematics. Let's continue to enjoy and develop understanding of mathematics together. Thank you.
Thank you, Professor Yuji Odaka, and thanks again to all the awardees for your sharing. Now we have come to the end of the first half of Mathematics Night. Please join us in Halls B and C for the buffet reception. And please pay attention, at 7 o'clock, we have invited 5 distinguished mathematicians and 7 student representatives to join a panel discussion called Student Ask, Master Answer. So now please enjoy your meal and looking forward to see you back here at 7 o'clock. Bye. Good evening, everyone. Welcome back to the Mathematics Night of 2026 ICBS. When it comes to mathematics, a lot of people, including myself, will think first of rigor and precision. But actually, mathematics is so much more than that. It's a language of beauty, structure, and elegance. Tonight, we will have the opportunity to admire and explore this through performances by several outstanding young musicians. To begin, let's give a warm round of applause for Zhou Xihe from Children College of Tsinghua University, who will perform the first movement of Beethoven's Badedic Sonata, Opus 13. Welcome, Xihe. Thank you, Xihe, for your splendid performance. Now let's welcome Professor Shin-Tong Yao, Chairman of ICBS, Director of CIMIS, and the organizer of tonight's Mathematics Night, to the stage for his address. Welcome.
Well, it's exciting to see all of you here. This year's ICBS is great. We see many important scholars coming here. And I listened to the talks by the winners of this year's award. I'm very impressed by their progress. And looking back, I think mathematics has gone through a long journey. Many basic structure of mathematics were understood much better. A new direction has been developed. Especially in the last 10 years, I watched the progress made by probability, made by combinatorics, made by category theory even, although when I was young, I never think much of category theory. But I have to say that it has done more than what I expect. Although whether it means that you will solve great problem, I'm not 100% sure. But I think we have to be open-minded for something that we don't like before. It may turn up to be useful and even important. But we did not lose the target that we want to solve. The basic questions, basic knowledge that we want to know is still about numbers, about geometry, about the rules that govern things together. We want to know analysis, how to build relations. All these are very fundamental, basic questions that human mathematicians would never forget. And I'm glad that many of them are also solved on the way when these new tools are developed. And classical methods has been strengthened. It is making strong progress. In the subject I have been very fond of, nonlinear analysis applying to geometry has been developing as strong as ever. Many important questions in geometry were solved. And I'm very glad to see many of the questions that I asked when I was young. That means 40 or 50 years ago. The problems are either solved or gradually being solved. To me, it's a great enjoyment. I make some conjecture, some of them based on my intuition, some of them based on some experience. When I make those conjectures, I probably do not have that much confidence. But when it is making progress, solving by many distinguished young mathematicians, step by step, I was really fascinated because it opened up my eyes. Although in those days, I feel that it should be true, but I did not know any ways to solve it. But gradually, many of our young mathematicians was able to open up the door one by one. Although some of them has not been completely solved, but it's still fascinating to see it. I find this a great joy of mathematics, that we make predictions, we can solve it, and solve it based on some new technology and some new interaction with different fields. And that's always amazing to me. For example, the subject of Calabi-Yau method would have been much narrower without the input of the string theories. In 1984, string theories decided that Calabi-Yau method is a good, important model for them. Ever since, they have been putting a lot of effort into it. So much computation, so much proposal, conjectures were formed. And up to now, after 40 years, many of these has deep insight into many branches of geometry, algebraic geometry, number theory, and representation theory. And it's infiltrated into number theory now. And I hope what Shao Jiang said today is good that number theory will gradually come into geometry and string theory even. And this is a beautiful combination of different subjects, different branches, mathematics and physics. And this is really a fantastic combination that I think nobody have been able to predict 100 years ago or a few hundred years ago. Of course, we are still following the great men like Riemann, like Gauss, like Euler, like Hilbert, but we are also making brand new progress, which I am rather proud to see in my lifetime. And I'm very happy. In the last 50 years, I've been in mathematics. I saw all this exciting development. These are all the development that artificial intelligence would not be able to achieve. I firmly believe that. So I've been interviewed by many reporters almost every day whether mathematics would be replaced by AI. I firmly believe that it's not possible. With this kind of creativity, beautiful problems coming up each year, fundamental questions are still being pursued and still being asked. This is a really fascinating time of our subject, which make me feel very proud of. And I hope our young students, postdocs, would be excited about all this development. Don't be discouraged by AI. Don't be discouraged by what the news media say that our field is dead. It's not dead. It's just moving into a new platform. We are going to build a much bigger version of our subject. So I hope we charge on. We will see much more development next year. Thank you.
Thank you, Professor Yao. Please remain seated on the stage. Mathematics bridges the abstract and the real, and its progress relies on the collective efforts of everyone here, Professor Yao, distinguished professors, young scholars, and all of you in the audience. Now let's move to our panel discussion called Student Ask, Master Answer. Let me first welcome our moderator, Professor Christopher Brav from CIMIS, to the stage. Welcome. Professor Christopher Brav research centers on derived and non-commutative algebraic geometry with notable contributions to shifted symplectic geometry and Donaldson-Thomas invariants. Welcome. Next, let's welcome Professor Kauchir Birkar to the stage. Welcome. In 2016, Professor Kauchir Birkar independently solved the important conjecture on the final algebraic varieties, the BAB conjecture. Currently, he is a professor at Tsinghua University. Next, let's welcome Professor Claire Voisin from Centre National de la Recherche Scientifique to the stage. Welcome. Professor Claire Voisin is an algebraic geometer recognized for her fundamental contributions to Hot theory and algebraic cycles. Next, let's welcome Professor Hongze Yao to the stage. Welcome. Professor Hongze Yao is a recipient of the Henri Poincaré Prize and the MacArthur Fellowship. He currently serves on the faculty at Harvard University. Next, let's welcome Professor Shouwu Zhang to the stage. Welcome. Professor Zhang is Eugene Higgins Professor of Mathematics at Princeton University. He works in number theory and arithmetic algebraic geometry, and he is the laureate of the Morningside Gold Medal of Mathematics. Next, please join me in welcoming 7 young students. They are Tan Renhao, Li Haoyi, Zhu Chenyi, Cai Ziyue from Tsinghua University. Please come to the stage. Chen Bowen from CIMIS. Hou Shengyu from Academy of Mathematics and System Science, CAS. Li Guo from the University of Chinese Academy of Sciences. Dedicated to pursuing mathematics along this beautiful yet challenging path, I believe they have many questions to discuss with the scholars. So now please allow me to hand over the floor to Professor Christopher Braff to host the session. Please, Professor, thank you.
Thank you. Let us begin with Hao-Yi Li, who has a question for Professor Hong-Tse Yao.
Yeah, thank you. I have a question for Professor Hong-Tse Yao. My question is, what is your perspective on the relationships between different areas of mathematics and how they interact with each other?
So you ask me what's the relation between different areas of mathematics? Well, I think that as a general question, that different area of mathematics is really the huge domain, and it's very difficult to say what exactly how they interact. But if you are willing to sort of look at even in a small a few mathematical area, they are very often that a discovery from one direction, they will has a huge impact to the other one. It's not just inside the mathematics. Even I think in the last 50 years, you saw a lot of impact from the physics to mathematics and going back from mathematics to physics. This is probably one of the most striking interaction between area and sciences. So this is already not just inside the mathematics. And the other thing is not just mathematics. Mathematics also has a huge impact on this computer science. So, areas called theoretical computer science is completely mathematical. And also not just that, if you look at nowadays how people formulate these statistics and also this artificial neural network is all in terms of optimization problems. So I know you are asking different area of mathematics, but think about even question like in artificial intelligence, the question, the way you formulate the question is still a very optimization question. Then you know that interaction between mathematics and the sciences are truly very fruitful and fundamental. Thank you.
Thank you. Thank you, Professor Yao. Let us continue with Chin-Yi Zhu, who has a question for Professor Claire Voisin.
Hello, Professor Voisin. Thank you for the opportunity. My question is, have you ever encountered scenarios where you required a solid understanding from areas that you're not familiar with or are not good at? How did you overcome this, and what motivated you to stand up to the challenge? Thank you.
I would say that, I didn't move very much outside algebra and geometry. But still, algebra and geometry, as I tried to show in my talk, is a very large field where you can arrive from in complex geometry, from the viewpoint of complex differential geometry, and then move to more and more algebraic tools. Most of my career, I have been studying inside algebraic geometry with some excursions in the field of symplectic geometry, that is related to algebraic geometry, to complex algebraic geometry via the complex projective variety is Keller, and the Keller manifold is symplectic. So I have been very interested in some, for example, the question whether symplectic, some algebraic invariants of projective complex manifold could be in fact of a symplectic nature. So I had a few works outside algebraic geometry. but most of my work was inside algebraic geometry, and it is true that I had to, my interest shifted progressively towards more algebraic questions, and even more arithmetic in some sense. You will see tomorrow in some sense, because I used to work originally mostly over C, thinking that that's enough, that there is enough to do. But finally, you see that there are many interesting questions over C that can be formulated in terms of algebraic geometry over a non-algebraically closed field. Typically, you can have a very interesting birational invariant of a variety that you can understand if you think to the variety thought as a variety over its own function field, which is tricky, but that's important. So what I want to say is that staying inside algebraic geometry, this is such a large field, historically, I would say. I had progressively to learn different viewpoints. It was not. It was more a sort of a continuous evolution of my interests, and it's not suddenly I decided to learn a different theory. No, it's more than I enlarged my interests, and so I also enlarged the tools, the set of tools that I could use. For example, you could believe that if you are interested in algebraic geometry over C, you may believe that you will never maybe need algebraic geometry over in a non-zero characteristic. And that is completely wrong. This is wrong historically, because for great results in birational geometry in algebraic geometry were proved using reduction to non-zero characteristic. But also, I mean, this idea, it is coming, I think, from Grothendieck. Algebraic geometry, this is enormous, but after all, it is a whole. And it's really in your interest to be able to do algebraic geometry over possibly any field, as I said, over C, but also then over a function field which is not algebraically closed. And maybe you do, by doing reduction to non-zero characteristic, you will catch some invariant. So what I want to say is that if you do algebraic geometry, you are more or less forced to learn progressively many things. You cannot, for example, do the economy of étale cohomology simply because over C you will do Betti cohomology. No, this is not the way that works. You at some point, finally, you are forced to learn more. And that was already, I think, in the mind of Grothendieck, this idea that really, to understand things, you really have to learn the different theories. That, I am not sure I answer your question.
Thank you.
Thank you, Professor Voisin. Let us continue to Guo Li, who has a question for Professor Xingtong Yao.
I would like to ask Professor Xingtong Yao a question. With the AI developing so quickly, what do you think are the most qualities to development, especially for the young mathematician and the PhD students? And I just heard one advice: don't be discouraged, and I want to get more. Thank you.
Are you asking me? Oh, okay. Well, as I just said, I think AI is very important and useful too. There are many references that I did not know. I can find it through AI. But AI basically collect all the knowledge by many great mathematicians up to now. But you want to make a new step that is not conceived by our previous ancestor, I don't think AI could do it. And we need a creative step and to make a big move to understand nature that we want to understand. And nature is changing. The way that we look at nature is actually dependent on time. In the old days, we do not know high-dimensional space. Now we know very well. We don't know much about manifold. We do not think manifold is there as an intrinsic object, but now we are very used to it after Riemann's discovery. All these are new concepts which AI would not be able to digest and make advanced steps. So what that means is that AI would be able to push what is known all the way, and many low-level type mathematics would probably not survive. But the upper level or the middle level would move up to a new platform that we become much more knowledgeable about the future and create better kind of mathematics. It's just like in the old days when computer was not invented, the people in fluid dynamics probably knows very little about nonlinear fluid dynamics because they do not know how to compute nonlinear behavior. Now we know more, but that's at a cost because when people use computers so often, they forgot about the powerful perturbation argument or previous argument that was used in understand fluid dynamics. So I think we do not understand fluid dynamics far better than before, although there's some aspects is understood now. So I think AI would probably do the same thing. It moved to a new platform. We understand some part of mathematics much better, but we start to forget what is important. And because most people are lazy, they do not want to learn what is not taught to them. So that's what I believe is going to happen. But AI will not replace human for sure.
Thank you, Professor Yao. Let us continue with a question from Shengyu Ho for Professor Kosher-Birkar.
Thank you. I want to ask a question to Professor Kosher-Birkar. So in our research, when we run into issues, how can we know that our method, whether our method just needs more work or it is just wrong and we need to try something else?
Yes, thank you for the question. Yeah, that's not very easy to answer, but maybe just from my personal experience, I can say a few words. First of all, if a problem is very easy to solve, then that's probably not a very good problem. So you should expect to get stuck at some point if you work on a really good and deep problem. So that is expected. Secondly, I think one is really only forced to be creative when you have to. And that's exactly when you think about a really difficult problem, or you try to connect different areas of mathematics in a non-trivial way. So if you are not stuck, then you are not forced to think and to be creative. So I think that's a good sign of a good mathematical problem is to get stuck. So this is not something to be disappointed. And the question is, well, what to do when you get stuck? So one, well, first of all, you have to think about this problem for a long time, depending how important the problem is. It could be weeks, could be months, could be years. So in my own case, for example, I have started thinking about the problem and solved it after like 12 years. That doesn't mean that I was thinking about the problem every day and night. No, that's not how it works. But I always kept it in mind. I thought about it for some period and then put it aside. I came back to it. So one thing is that I think it's good to work on a really good, difficult problem for a few months. before giving up. If you see any sign of progress, then it means that you are doing something right. So it's better to continue. But if you are completely stuck and there is no progress at all, then it's a good time, I think, after a few months, just to put it aside. Maybe not forever. You can come back to it later. So one thing can happen is that new ideas are developed by yourself or maybe by other people, and then later you will realize that these new ideas actually can help you to solve the problem. So again, this happened to myself. I had problems, but I started even when I was a PhD student. I thought about it for a long time, not much progress. And then later I developed a theory which didn't seem to have anything to do with the original problem that I was thinking about. But then after a year, I realized that it's actually one of the key ingredients of solving this problem. So just putting aside the problem for a while and coming back to it, I think is a really good kind of way to deal with getting stuck. But if you do this for a few times and there is absolutely no progress, well, either you are working on the wrong problem, or it's just that it's not the right fit. Maybe you don't have the right techniques and background to think about the problem. So I think also just because a problem is famous is not a good reason to think about a problem. You have to be really, in some non-trivial way, passionate. You have to be fascinated by this problem. It doesn't really matter how famous it is. There are really extremely good, deep mathematical problems that people outside the area have never heard of. And this is related to a few things, why this happens. Some people in some areas, for example, my field, which I work mostly in birational geometry, we are just not good in advertising our field. We don't really have the kind of people to, write good things and attract the attention of the wider community of mathematicians. But we have really extremely deep, difficult, and really important problems in our field. We are just not good enough to advertise it. So if you look at, list of famous math problems with a lot of, prizes to solve them, you may not see this problem. It has to do with the culture of mathematics. So anyway, I think leaving aside the problem, coming back to it, look at it from a different angle, and of course, learning some other new techniques is a good way to deal with this getting stuck. Okay.
Thank you. Thank you, Professor Birkar. Let us continue with Renhao Tan, who has a question for Professor Claire Voisin.
Thank you. My question is for Professor Claire Voisin. When a long period of work, research, study leads to a dead end, how can you keep motivated? And finally, how can you push forward? Thank you.
It's for me, I believe. Yeah. So I'm not sure I understand your question. So you ask how I can stay motivated in doing research in mathematics?
Yeah, well, long period of work
leads
to a dead end. Yeah.
I mean, you are asking over my whole career or for a specific research on a problem?
Maybe could you share some special experience or some special advice for our students how to overcome the difficulties in the research?
I think that co-chair already addressed this. Choosing the problems and staying working on the problem. It's hard because well, of course, I can spend several months working on the problem. It's not how to say, I am brave, I could continue, but sometimes at a certain point you start repeating the same arguments, and in fact that means that your brain does not continue to work on this problem. So that's why personally I tend to be rather more opportunistic. I tend to go in a direction or in a problem when I see at the beginning that there is something new in what I want to say is that in many cases it's really a bit I mean it's not really productive to just to face a given problem simply because you like it. If you don't have a new idea or something that starts you on the problem, the danger is simply that nothing happens. So, and personally, I also like very much the unconscious path, which is the fact that our brain works even when we are not really aware. So you work, I do research every day, sometimes on problems that I am not able to solve. And it frequently happens that suddenly I get an idea on a different problem. So sometimes I just follow catch that direction. It's not simply the dispersion, because sometimes this idea is on a problem that I had studied previously without an idea. So I like the fact that I have been thinking on this problem at some moment. I had no idea, but typically questions about rationality of Fano varieties. The criterion of the existence of a decomposition of the diagonal. I knew that criterion when I was in a postdoc, and at that moment I thought that would be very nice to prove the irrationality using that criterion, but I was unable to go further. Unfortunately, I haven't pursued that question at that time. And finally, in 2015, I introduced a method using this was called a specialization method, which allowed to prove the non-existence of decomposition of the diagonal for varieties which were very simple, some Fano trifolds, for which certain previously known invariants due to Artin and Mumford did not exist. So what I want to say is that I knew the problem was interesting. I knew the notion. I knew that for more than 20 years. And I more or less, by some, I cannot even tell how this happens to me, but suddenly I had the possibility to make to make progress on that question. So personally, I find it almost impossible to face a problem, even if you like it. For example, the Hodge conjecture, of course, for me it's the most important conjecture. But I must say that I have no idea on the Hodge conjecture, so officially I don't work on the Hodge conjecture. I mean, it's dangerous because you could stay stuck for your whole life. So I am more in the opportunistic style. There are many beautiful problems, some of which I would like to solve, But if I don't have this moment where I feel that maybe the things are going to move, I think it's dangerous to try. Of course, you can try for a few months, but I mean, sometimes we are stuck. I mean, because we need maybe a long period of time, or maybe we need that some idea comes to you. I don't know how, but.
Thank you, Professor Voisin. We have about 10 more minutes, so for 3 more questions. So let us try to be concise going forward. The next question is from Baowen Chen for Professor Hongze Yao.
Yeah, thank you. I deliver my question to Hongze Yao. Just now you mentioned the correspondence between mathematics and physics. And I think there are a lot of comparing phenomena in mathematical physics. Like during your talks in the morning and afternoon, there are Wegener's pictures, Anderson's pictures, and later the Dyson interpretation of some Riemann zeta functions. And as a beginner of researcher, how can we choose to begin with? Like, shall we decide to establish some toy models, like rigorous, simple models, or shall we find some inner correspondence between different pictures, or shall we try to attack open questions, or shall we dive deep into the mathematical details, like how to control the complicated analysis behind the pictures? Can you give me some comments or recommendations? Thank you.
I think in the beginning, for somebody who has almost absolutely no experience, it's almost impossible to find a problem. For example, when I was a graduate student, of course, I have no ideas what exactly the problem one can find. So in the beginning, you just have to talk to some senior professors, and I think this is actually unavoidable. But the question is, once you have some experience and your advisor in various sense and give you question to think about, and now how do you decide that what to do next? Sometimes it's quite it's not clear. You for example, it can happen that the problem your advisor gives to you, it cannot be solved at the time. For example, when I was a postdoctor, I think a 2/3 of the problem given to me, I think it's more than 2/3, probably 80 or 90% of the problem I was assigned to do. It turned out nobody solved it in the next 20 years. So it's not just nobody solved in 20 years, it's probably in the next 10 years there was no progress. And so sometimes you, but on the other hand, once you start to think about a problem, you look at a problem, then you can start to ask new questions. So I think it's very important to learn how to ask questions, because typically a question, even if you cannot solve, you still can think about if there's some other related question that you can ask, and it looks easier and you might be able to make progress. I think fundamentally this is the most important question in my view of doing research. So I remember my advisor, Ada Lieb, when I did my thesis, he gave 2 problems. The first problem, he asked me to prove an equation has no solutions. And it turned out at the end I constructed a solution for him. And then a second question was he asked me to do some problem related to black holes. It's a quantum mechanics question. Anyway, I worked for about a whole semester. I made absolutely no progress. And then so at the end, it's almost near Christmas, and Lieb asked me that, I mean, what did you, so he wanted to talk to me about the question. And then I talked to Lieb. I said, well, look, I mean, there was a much easier question I couldn't even solve. And when he saw this question I could not solve, he was very happy. He said, well, this one I'm able to solve it. And so he showed me how to do this problem. And at the end, we start from this step and try to find a way to solve the original problem. So even though your technique may not be very strong as a student, and so you still can think about it and try to ask various questions. And of course, you need guidance, you need senior people to help you. But I think this to think about what are easier question and relevant you can solve is one of key steps. Thank you.
Thanks. Thank you, Professor Yao. I'm afraid we have time for one more question. The last question is from Chenyi Zhu for Professor Shouwu Zhang.
Okay, thank you, Professor Zhang. So this is another question about artificial intelligence, but probably from a different perspective. So in recent years, we have witnessed an increasing number of questions being solved with the aid of artificial intelligence or even by it. And what do you think this means for the mathematical community in terms of our research methods or directions? And what we as students of mathematics should pursue in this new era? Thank you.
Wow, yeah. I mean, you ask all the philosophical questions, now you ask a more practical question. I'm going to retire, so I don't really worry about that. Okay, so I think you have to use it, right? I mean, it's very powerful. It's not a question. You have to use AI in your research, because it's just like you take a train or take an airplane, travel from one place to other place. But on the other hand, if you just take, for example, if you just walk from your office to your home, you're not supposed to use AI. You should use the foot. Use the foot can become more healthy. So you should be very careful to use AI, and use AI make you more smart, not make you more stupid, right? So this is quite important. Other than that, I really don't know what to do. For me, I think, for example, the slides I prepared use AI. That's very nice. They're very fast, much faster than myself. And when I do mathematics, I'll be very careful, because I think human beings are very special. We are very short life. We have our own way to view the beauty. So as Professor Yao always asking questions, ask problems. It's a kind of a thing, our own territory. But I welcome AI can help us to solve problems, in particular long problem. And even in mathematics, some problem is solved. Doesn't mean we understand the solution. Not only the like a four-color problem or the classification groups, even in number theory, the many proofs is very long. Every time I teach the class, for example, Galois theory, when I taught the class, I completely forget what the Galois theory is. It means that we know the theorem, but we don't know the proof. Class field theory, for example, is beautiful, but I can never understand what the proof is. Even I can write everything on the blackboard. So then I think AI is going to create even more problems. They prove the theorems, but you don't really understand the proof. You understand the logic step, but doesn't really know. You cannot really tell your kids in half hour what the proof is look like. So I think this it's a different thing. In the future,
I can imagine they're going to have, like physics, you have theoretical physics, experimental physics. Maybe we come to one day called theoretical mathematics or experimental mathematics, right? So the theoretical mathematics is going to propose conjectures, propose questions. Experimental is going to give a proof. But even the proof, there's a better proof or worse proof. So I think that your younger generation going to next, 10 years, maybe 5 years, you're going to see a lot of changes. But it doesn't matter. You have to trust yourself, right? We are a human being with involved maybe 20 million years. So we have something. I don't believe AI can catch up in a very short period.
Thank you, Professor Zhang.
Sorry to interrupt, Professor Bravo. We have more questions from Cai Ziyue to Professor Culture Birkar. We have time. Thank you.
So Ziyue Cai has a question for Professor Birkar.
Okay, thanks for the opportunity. My question is for Culture Birkar. We know beyond solving questions and proving theorems, mathematical research requires much more kind of intelligence. So in your view, what's the most important aspects of mathematical intelligence that today's AI benchmark fail to match? For instance, the ability to ask good questions or to develop new concepts or decide which ideas or directions are worth pursuing. Thank you.
In relation with AI, that's the question. Okay, so I have been kind of interested in AI even 6-7 years ago. I remember I attended some science forum and I even gave a talk about machine learning, but I didn't really learn enough about AI, so I'm not an expert in AI at all, but I have been using AI, especially more recently. Until the last few months, to be honest, I was not really that impressed with AI. I was impressed in the sense of what we had 5 years ago. You just had Google to search. That's basically the only way we could try to find references and maybe find some website or some article, which is not very convenient. But AI does this kind of thing much, much better. You can actually talk to the AI just like you're talking to a person. If you talk to your colleague, maybe after 1 hour, 2 hours, they get tired and they are not interested anymore. But the AI, you can keep asking questions for a long time. So in that sense, it was very impressive. Something that we didn't have before. You can actually talk to these machines. But in terms of the answers and so on, I was not really that impressed. They gave a lot of wrong answers. It's just very, very basic. But it's only in the last few months that I have seen more impressive stuff from AI, probably because I started to pay. Before that, I used the free versions and they didn't really work. So what has changed then? What I have been impressed in the last few months is that they are getting much better in a technical sense. That means that once they learn the tricks and all the little things in a subject, then you can ask them to do a kind of routine and even kind of non-trivial things. So one of the things I do very recently is I say, well, I have this lemma. I give the statement of the lemma and I give just 1 or 2 sentences, ideas for the proof, and I ask the AI, well, write the proof for me. And it does it, because this is one of the things I really never enjoy too much, writing all the little details. Now I can use AI to write the details for me. So in that sense, it's really getting very, very useful. And also, if I make a mistake sometime, it actually tells me, well, there is a mistake there, if it's not very subtle. So it's extremely useful. But to be honest, on the other hand, I have not been impressed at all in the sense of creativity. Any point where it needs some kind of new, even semi-new idea, it just doesn't do anything. So its strongest aspect, I think, is that it knows pretty much everything in math. If you need anything which has been published recently or 50 years ago, it might be some little paragraph in some paper, it can find it very quickly. Obviously, I could never do this kind of thing. You cannot search like thousands of papers at once, but AI can do it. So in that sense, is really, really strong. So until I see AI do something really highly creative, I would not believe that it can catch up with humans. But I'm not saying that it can never do. We don't know. Maybe 5 years later, we will see different machines with much more powerful. Maybe they can even get creative. But so far, I haven't really seen at all. So I think just continue mathematics as you did before. You can use AI as well to help you with the routines and with writing, with presentation, for example. So one of the things I really hope that AI will do is to write paper, I mean, in the sense of to improve the presentation, because some papers are just painful to read. But AI can actually make it way, way better. So I don't think you have to kind of change the way you do mathematics in the sense of understanding, in the sense of asking questions, whether there is AI or not. I think you still have to do this kind of thing to do very good mathematics. And to go far into the future, to be honest, I don't even really care so much if AI can catch up with humans. So what? I mean, cars can catch up with people. People still go to run marathons. Computers could beat people playing chess already 2 decades ago. And now in almost every city in the world, there is a chess competition. Why? Because they want to play chess. Suppose I can do, I don't know, even mathematics much better than us. We still want to do math. Why not? So I don't see mathematics being dead and so on. I think the only maybe danger is jobs and funding, whether governments will still continue funding mathematicians. That is a different story. That may be affected, but I don't know when. Thank you.
Thank you, Professor Birkar. I would like to thank all of the students for their stimulating questions and all of the masters for their thoughtful responses.
Many thanks to our professors and students for the wonderful discussion. Please take your seats in the audience have a rest. Thank you. Now we have a very special segment. On July the 23rd, Professor Hong Wang and Yu Deng were awarded the Fields Medal. This is truly a remarkable achievement and immense inspiration to all young scholars who are deeply committed to the pursuit of mathematics. Although Professor Deng cannot be here in person tonight due to the scheduling conflicts, he will kindly join us online. So now please welcome Professor Deng for his virtual presentation. Deng.
Hi, good morning.
Can you hear us and see us clearly?
Yes, I can.
Yeah, over to you, Professor Deng.
Okay, thank you. Thanks for the invitation. It's very nice to be have this chance to have a little bit discussion, have a little bit of talk. Yes, I prepared something, concerning what I have been doing, the SPDs, critical problems. But I guess since I have 5 minutes, I'll kind of talk kind of more generally. Yeah. So I mean, I've been hearing discussions on AIs like in the last 10 minutes, and because I mean, I was at the ICM, and because like basically every discussion I've been meeting with people, having lunch with people, every discussion we had kind of involved AI like in one way or another. So this is kind of very interesting phenomenon. I mean, I have to say that at this time, like in my subject, like in these PDEs, SPDEs, like probability, these kind of things, it hasn't been kind of affected too much by the AIs. I mean, I've been trying to use these AI tools, and like in my problems, in the open problems, like that have been considering, and they have not so far. They have not been so helpful. But I guess maybe that will change. I don't know. Like already it has been pretty strong, like in some subjects. I mean, in combinatorics, like maybe in algebra geometry. I don't know, but yeah. So they are developing very quickly. So maybe I want to say something, just a little bit about basically the future. I mean, no one can predict the future, but I think so. At this time, I mean, what the AI can do is kind of some kind of like a relatively small problem. I mean, so first of all, it has been kind of more and more the case that the difficulty of a problem, for AI is kind of not the same, like as the difficulty of same problem to humans. Like for example, this unit distance problem, or this counterexample for the Jacobian conjecture, it's something that people have been working on. I mean, maybe not that many people have been working on, but at least people have been working on for a long time. They haven't been able to solve it, but the AI could solve it like very quickly. Okay, within like some reasonable effort. On the other hand, there are questions that AI still cannot do. I mean, so for example, like this problem in my field, so there are problems I've been asking the AI to do, like some problem which I certainly know what to do. I certainly know how to solve, like by extending the method of some of my recent papers, something like that. I asked the AI to do, but AI didn't kind of didn't get like a quite satisfactory answer. So I think this is an interesting thing, that if the difficulty of a problem, for human is not the same, as the difficulty of the same problem to AI, then like in the future, how would we kind of how we judge like the difficulty of the problem, how we judge the value of the work? I think this is one of the things. And then, of course, there are kind of like more kind of future questions where maybe in the future AI can get stronger. I mean, it can produce even longer proofs. So now AI can produce like a 10-page, like 15-page proof. Now maybe in the future it can generate even longer proof and correct proof. This is very hard because you need every single step to be correct. It's not like playing Go. You just like have 99% winning rate and you are good. But here, like if you have one single step is wrong, then you're wrong. But anyway, so let's say in the future AI can kind of get stronger, generate even longer proofs. But then I guess what happens is that for now, even now, like we are kind of we are build our mathematics, build our research based on theorems. Okay, based on theorems we know. They are also kind of very long theorems with very long proof, like very difficult theorems. So then in the future, if AI can generate longer proof, then I think what happens is that we'll just add these theorems into our collection of theorems, and we'll start from there and see what we can have. So I think, yeah, this is some of my reflections, like from today's, discussions and all these early discussions I had with AIs. Yeah, I mean, it's I think I'm sure many things in mathematics will change, like already now, but maybe in the future, like with even stronger AIs, like for example, as I already said, the criterion of judging a theorem, judging a work might probably change. And of course, there are all these funding issues and different things. But I think, like in the end, I think like we'll still be doing mathematics. Like like no matter what happens. I mean the AI will get stronger, but that means the human will get even stronger, and then AI will probably kind of also improve and so on. So yeah, so I guess everyone has been talking about AIs, maybe I also share a little bit about my thoughts. Okay, so I guess that's probably it. So thanks for the invitation again. So I hope you have a nice conference.
Many thanks to Professor Deng. To make the most of this precious moment, we are pleased to set a Q&A session. We will open up several questions from scholars and media. So the first question turn to the academic side. Any question for Professor Deng? Yeah, please.
Um, 10 years ago, there was a similar panel of experts, and there was a discussion involving Maxim Kontsevich, and the discussion was about AI, which was strange 10 years ago. And Maxim, somewhat surprisingly, said that he believes that AI in the future can do mathematics better than people. He believes it's possible even within his lifetime, which is, again, a very bold prediction for 2015, but whatever. Then I guess Terry Tao asked him why is he not working on this, and he said it would be immoral. So what is your take on the moral side of using AI and developing AI?
Okay, thank you. So so there are moral issues.
恭喜取得了这么好的成绩。我来自中央电视台新闻中心。我的问题是，刚才大家其实都在围绕 AI 在问问题，那其实我的问题也是围绕 AI 的，就是对于我们现在的年轻的学习数学和感兴趣数学的这些学生们来说，在未来，尤其是面对 AI 的冲击是最大的，所以他们应该如何在现在做好与 AI 去共同进步的准备的同时，如何更好的去学习数学？你有什么样的建议吗？谢谢。
Hi, thank you. So should I understand in Chinese or English? And learn to play with it, learn to kind of maximize your efficiency work with it, and then you can choose what to do. There are many students that may move from math to AIs. This is fine. You can choose whatever you want to do, but I think there's still always this joy in doing mathematics, and I guess my suggestion is to kind of to prepare yourself by kind of getting familiar with AI and getting familiar with all these technologies, as well as developing the strengths yourself, and we'll see what happens in the future. It's not clear at this point, but we'll see.
Thank you so much, Professor Deng, for joining us online. We're looking forward to seeing you in person next time. Goodbye.
Thank you. Bye.